Hello, I'm Aknur Karabai, Research Assistant at the Institute of Smart Systems and Artificial Intelligence, and in this video we'll cover Random Sample Consensus, or shortly RANSAC. Let's consider autonomous car navigation in cities. Sensors are used to detect signals from the environment to identify moving and not moving objects such as ground level, lanes, road edges, and etc. And one of the common issues is the separation of the noisy data from the robust signal. For instance, consider a wall near the road edge. Noise may shift the detected edge and car might crash into the building or pedestrian. And in order to address such problems, random sample consensus algorithm deals with a robust estimation. Suppose we are given the data from sensors to detect the ground line. Now let us try a common line fitting technique, least squares regression. The vertical offset shows the error between the approximated line and the data. Least squares method determines the best fit for a set of data points by minimizing the sum of the offsets or residuals of points from the plotted curve and mathematically expressed as follows. Error E is equal to the sum of square differences of yi and approximation function f. For this problem, we use the equation of line as a function f of x equal to b0x plus b1. By substituting the equation of the line into the cost function, we get error E as a function of b0 and b1 equal to sum of square differences of y of x minus b0x minus b1. The red line here shows the approximation obtained using least squares regression. This method considers all the data points and it's sensitive to outliers. Outliers are highlighted as red. These are observations that deviate too much from others. The outliers are usually generated by different mechanisms from other observations and considered as a noise that needs to be removed in order to make more reliable prediction. The trend for the fitted line should have been along the inliers, green data points. Inlier is an observation that is within the underlying probability distribution function and fits the predicted model well. So in conclusion, least squares regression is not robust for a dataset with many outliers. Now, let's consider a different method, random sample consensus. Random sample consensus, or shortly RANSAC, was invented by Fischler and Bollas in 1981. RANSAC is an iterative and non-deterministic algorithm that has been first used for location determination problem and now have been widely integrated in computer vision. The algorithm performs well even in the presence of outliers in the dataset. The main idea behind RANSAC is a voting scheme. We have two main assumptions. The first, outliers or noisy data points do not vote consistently across models. And secondly, ratio of inliers to outliers is sufficient to predict the correct pattern. Now let's have a look on the RANSAC algorithm. So step 1, we select randomly m points from the dataset of points to determine the model parameters that fit the data. Step 2, we compute the parameters and get the model. Step 3, we check all the data points to find all the inliers to the model within the error tolerance threshold, and if the inlier to total number ratio exceeds the predefined minimum valid consensus threshold, then we correct the parameters with the identified inliers and stop. Otherwise, we repeat steps 1 to 3 n times until we reach a valid consensus. Because we use a linear function to identify the ground line, we use randomly 2 points, m equal to 2. So let's have a look on trial 1. The randomly selected points are highlighted in red. We have estimated the line that crosses these 2 points, and by plotting error tolerance threshold lines, we can see that the ratio of inliers to total data points is equal to 0.3, which is not acceptable. Now let us try another trial. We have selected randomly another 2 points, estimated the line crossing these 2 points, and by plotting the threshold lines we see that ratio is equal to 0.4, which is also not acceptable. So trial 3. In this case we see that the ratio of inliers to total data points equal to 0.6, which seems to be okay, and for this problem is bigger than minimum valid consensus threshold. Now we have recomputed the line with identified inliers. Well, how to select the number of iterations n? N can be set to a large number, so we can assume that at least one combination will consist of inliers. To derive the equation of n, let's start with k. Let k denote the probability that a randomly selected point is an inlier. So consequently, 1 minus k will be the probability of random point to be an outlier. So the probability that in one selected sample set all points will be inliers is p equal to k to the power of m. And now that in one picked set of samples there will be an outlier becomes 1 minus p equal to 1 minus k to the power of m. So for n iterations, probability becomes 1 minus p equal to 1 minus k to the power of m, everything raised to the power of n. And by solving this equation, we can derive the equation for n. The table here shows number of iterations n required for different outlier ratios. Let's go back to the example with identification of the ground line. We have selected 2 points, so m equal to 2, and proportion of outliers was 30%, 4 out of 10 data points. So for this example, the average number of iterations required until we reach a valid consensus is 11. Studies show that the proportion of outliers in the dataset should be less than 50% for the RANSAC to work properly. Now let's have a look at other critical parameters. One of them is error tolerance threshold. A suitable threshold value should be fine-tuned. So if the threshold is chosen too large, some random sample line considered as valid consensus will include some outliers. As an example, let's consider a dataset for identification of the ground line. If we set error tolerance threshold for this problem too big, we may end up with completely different pattern accepted as a valid consensus. So in this case, we have obtained inliers to total data points ratio 0.7. And in the case of too small threshold, RANSAC will not reach a consensus that will include all inliers, even if it chooses 2 inliers for fitting the line. Let's have a look at the same dataset. As we can see from the plot, there might be other cases that will result in the same ratio of inliers to total data points as the true one. Next critical parameter is minimum consensus threshold d. If d is chosen small, some random line that fits a portion of the samples would be considered as a valid consensus. And on the other hand, if d is chosen too large, even a good example wouldn't pass the minimum consensus threshold, and no final model results will be found by RANSAC. There are several advantages of RANSAC. It is easy to implement and applicable to large datasets. And RANSAC performs very well and deals with noisy data and outliers. There are also some disadvantages, such as many parameters to tune, and tuning may take long. And also, RANSAC requires reasonable inlier to outlier ratio, usually should be greater than 50%. RANSAC can perform well in object feature translation, homographic transformations, detecting vanishing points, identifying facial landmarks, and identifying similarities in images, etc. RANSAC can be extended using importance sampling and maximum likelihood framework. Importance sampling is a variance reduction method. It can be used to analyze one set of data while sampling from another. Maximum likelihood framework is a way to treat a problem as an optimization or search problem, where we seek a set of parameters that results in the best fit for a set of data samples.